the next section we're going to be studying in class deals with inverse functions. This is section 1.5 from your book, and these notes are posted on our Edmodo page. But let's go over these together in case you don't quite understand it. A function can be represented by a set of ordered pairs. If we take this function, x plus 4, we could write it as a set of ordered pairs. If you notice here, all of our x values could be 1, 2, 3, 4. And then our range values, which is represented by the set B, could be 5, 6, 7, 8. Or more traditionally, we look at that as an ordered pair, which is represented right here. One ordered pair is 1, 5 when x is at 1, y is at 5. When x is at 2, y is at 6. When x is at 3, y is at 7. When x is at 4, y is at 8. And those are all values that come from this function f of x, x plus 4. To find the inverse, we can interchange the first and the second coordinates. We can basically flip the x value and the y value of each of these ordered pairs. So you can form the inverse function of f, which is denoted by f to the -1 power. Now, we've seen this idea before with inverse functions. Maybe you're thinking, oh, that's right. When I take the inverse of tangent, I write tangent to the -1. That's because those are inverse functions. This notation denotes that it's the inverse to the f function. And once we take the inverse, it becomes a function from set B, so starting with our range, to set A, which is our domain. So this is written like this. If I take the inverse of my function f, which my function f was x plus 4, I get x minus 4. And so now, as ordered pairs, notice all of my x and y values change. Now when x is at 5, y is at 1. When x is at 6, y is at 2. X is at 7, y is at 3, and when x is at 8, y is at 4, which is the exact opposite from what we started with. Notice the x's and the y's switch. Because of that, the domain and ranges of these functions will also switch. Note that the domain of f is equal to the range of f inverse and vice versa. Okay, so when these x and y coordinates switch, the domain and range will also change. Notice that the f and the f inverse function have the effect of undoing each other. In other words, when you form the composition of f with an f inverse, or the composition the other way, f inverse with f, you obtain the identity function. In this case, it would just be x, because these are linear functions. So let's put this to the test. So if I take the composition of f and f inverse of x. That means I'm dropping f inverse function into the f function. So I'm taking the inverse, which is x minus 4. I just substituted x minus 4 for this notation. And I put that into the original function. The original function is right here. X plus 4.
Pardon this interruption. Mark Cruzon, if you're in the building, please report to the front lobby. Your ride is here. Mark Cruzon, please report to the front lobby. Your ride is here. Thank you.
So I substitute this value, x minus 4, the inverse function, into the original function. So instead of writing that x there, I replace it with the entire value of x minus 4. I get x minus 4 plus 4. Notice the -4 and the +4 are inverse values, so they equal 0, so we're left with just x, which is the identity function. The opposite is also true. If I take the composition of the inverse of f of x, we still end up with a value of x. Moving on, let's look at an example together. We can show algebraically that these functions are inverse functions of each other. And I'm going to see if f of x and g of x are inverse, then when I take their composition, f of g of x, it should equal the value of x when I take their composition. So f of g of x, so I'm going to substitute all of the function for g into the f function. So instead of writing an x here, an x cubed, I'm going to write this entire g function. So it will look like this. 2 to the cubed root of x plus 1 over 2 cubed minus 1. Now hopefully you know that the cubed root and the cube are inverse functions. So the cubed root and the exponent of 3 will undo each other and give us a value of 2 times x plus 1 over 2 minus 1. When this is simplified, my 2's will cancel. I'll have x plus 1 minus 1, which does in fact just equal x. You notice all of the operations have an inverse operation. This is being divided by 2. Well, here we're multiplying by 2. Those are inverses. This has a plus 1. This has a minus 1. Those are inverses. This has a cubed root. This is a power of 3. Those are inverse operations. The last thing on this page says the graph of f is a reflection of the graph of the inverse in the line y equals x. Let's take this example and see exactly what that means. If I look at these two graphs, the first graph in red is 2x cubed minus 1. The graph in blue is the cubed root graph of x plus 1 divided by 2. Notice that they are just a reflection of the line y equals x. And think about how we got the inverse originally. We switched the x and the y coordinates. So when I graph in the line y equals x, that green line is the line y equals x, I can visually see that these are inverses, that they're a reflection in that line y equals x. Let's look at another example graphically. We need to verify that the function